We now invite Dr. Josef Uher back to the stage to present his talk titled Radix Portable Multimodal Robotic Scanner. Dr. Uher is a distinguished physicist and expert in photon counting detectors with extensive contributions to X-ray imaging and computed tomography. The audience is eager to hear your lecture. Dr. Uher.
Yeah, okay. So once again, good morning. So I would like to now show you a little bit more about our approach to the robotic system. Again, guys, we're too big. Let me go back a little bit to the history again. So I already told you that for us the robotic journey started 2016, but in reality there is some history before that as well, because we started with the whole like radiation imaging business as students, PhD students and postdocs at Czech Technical University. For me it started 2002. For Jan Jakubek, who will be talking later, it was at the late of 90s, and there are more people in this room who are involved in this as well. The point is that over that 15 years of building detectors, we learned a lot how to use them, how to operate them. We were building systems around them, and everything led to a point when in 2013 we established a company, or actually Jan Jakubek and Josef Uher started a company of Advacam, which is commercializing the technology of radiation imaging detectors, photon counting detectors, so new generation of X-ray imaging devices. And because we had that experience also in integrating these technologies, we started Radelitica. And original idea was that it will be a general system integrator for these detectors, but because I visited this friend of mine, we realized that it's much more interesting to focus really on the robotics and combination of robots. This radiation or X-ray imaging business is also inside art. That's a third of our companies. That's a kind of spin-off which is focusing on inspection of art. So there was a question about inspecting sculptures and art pieces. So that's what we do in Inside Art, and there will be one more talk in the afternoon focusing on that. Nevertheless, so we started 2016, and as I said before, we were developing the idea further and further up to a point where I would say we have now like a mature enough system that we can deliver to our customers, and we have already machines installed at our customers in variety of industries. Very surprisingly, the very first customer wasn't aerospace, wasn't automotive, nothing like that. It's a company here in Czech Republic, PSI, which builds like automatized greenhouses for phenotyping. So they study growth, or they build greenhouses to study growth of plants. And they measure all sorts of parameters of these plants, and they wanted to have X-ray imaging stations. So that was our first customer. But now the focus is mostly on space, aerospace industries. So the basic principle, I can probably go very, very, very quickly through. Everybody in this room knows. So X-rays is a game of shadows, so we are also measuring shadows. The difference is that we have the photon counting detector on one of those robots, and photon counting detectors bring lots of advantages for X-ray imaging, better image quality. They are opening new applications which were not possible with older types of X-ray imaging detectors. Jan Jakubek will be talking about much more about photon counting detectors in detail later. So I don't want to dive into detectors. Nevertheless, we are using smaller robots. We are using universal robots, and we are trying to make the system portable. Why portable? So computed tomography is nowadays very well established method in medical field, but also very much in industry. And there are all kinds of imaging systems. You can have high resolution for small volumes. You can have large volumes. You can have all kinds of industrial CT machines including the robotic, as we heard from Gabriel just minutes ago. The point is, all these machines require that the sample goes to the machine. So you have to, you can inspect things that fit into the the CT system or the cabinet that you have around it and so on. However, there are many objects that are way too big to fit in any kind of CT machine. So in reality, the need is to make the system smaller again and use some different or clever approaches how to enable the inspection on such a large object, such an aircraft or spacecraft. So here you can see exercise that we did for our partner, Orličan company. It's a manufacturer of ultralight aircrafts. Actually, Czech Republic is very strong in production of small aircraft, sport aircrafts. About 1/3 of these aircrafts worldwide are built here in Czech Republic. So aerospace industry is quite strong. And what you see, or what you saw in the video there, the guys are packing the system, loading it into a small van and bringing it to the factory. This is a newer exercise that we did last year. This poor aircraft had an accident on during the final, let's say, phase of the landing. The engine cut out because there was a problem with fuel delivery. And the pilot had to crash land about 200 meters short of the runway. And during that landing, the landing gear, which was already out, ripped off, broke, and hit the skin from beneath of the wing. The skin detached, and the right wing hit the ground. And so we knew that there is like a detachment, that the skin is detached from the main spar. So that's the support that is running through the aircraft. So we knew that it is detached, but the question was, is there any defect inside the main spar? Because that would mean that's the end of the fuselage. It has to be thrown away. And so we packed the system and took it to the middle of nowhere. It's like a garage somewhere in mountains, in Czech Republic, where they are going to fix the aircraft. And we had to improvise quite a bit because this was really not a spot for like X-ray imaging. However, you can see the flexibility of the system. So we are setting up the machine, we are calibrating the position of robots mechanically in this case, but we can do it with X-rays, attaching source and detector and placing both near the location where we need to or we would like to measure. Then doing some more calibrations and setup in the software and then running the measurements. So you see now the robots are measuring the main spar, so that's where... Do we have a laser pointer here? Yeah? Or which one is it? Yeah, okay. So the main spar is actually here, yeah? So that's a support that runs through the aircraft. And there was a question about radiation protection. So in this case, it was combination of shielding and distance. In circumstances like here, it's relatively straightforward. We helped ourselves with some like LED screens. You can see them here. But in reality, about 15 meters away from the place where we were measuring, there was background. There was no radiation present. That's one thing. Second thing is that because we have the photon counting detectors, they are sensitive. They are more sensitive, so that means we can use weaker sources, and again, the radiation protection is easier. So here is one of many scans that we did on this aircraft. So that's the main spar. The good news for the owner was that we did not discover really any damage that would be correlated to the accident. However, there were lots of strange things happening in the layering of the carbon fiber in the material. This is yet another similar accident. Here, the landing gear closed by incorrect setup of the aircraft. The pilot didn't go through the checklist at the beginning. That's why it's so important to go through the checklist. So he didn't do it correctly, and when the aircraft was just lifting off, the landing gear, because it was set to close, started to closing. It has automatic closing, but because the aircraft wasn't yet flying properly, or enough, it landed up on the belly and it was sliding on the grass, and it got some damage. So again, the same story. We took the system and we brought it to the hangar where the aircraft is placed, and we did our exercise of calibrating things, and we measured. So there were some cracks that were visible on the surface, but unfortunately we discovered also many others that were hidden in the structures. And because it's quite important part of the fuselage, it seems that this aircraft has a bad luck. You know, they may have to throw it away. It will be difficult to fix it. Now, okay, so back to robots themselves and the properties of imaging. So one big plus of photon counting detectors for non-destructive testing, especially in aerospace, is that the photon counting detectors deliver broad dynamic range. So what does it mean? Is that in a case like this, it's our test object, a dry rose, where we have glass vase and a dry flower. That's something very difficult for X-rays, because you have very low attenuating structure here, but you have relatively highly attenuating structure there. So standard X-ray imaging devices would have a trouble to show everything in one shot. You would have to take multiple shots very often, and it's not that easy. But with photon counting detector we can do it, which means in combination with robots we can really scan difficult objects, in difficult situations. This is an example from art. I like it a lot because if we look here, so this is a silk on the puppet, and this is the structure of the nail. So you can see it's a massive difference in material properties from silk to steel in one picture. In terms of the resolution, detectors themselves can resolve 50 microns. I think Jan will be talking about it. However, when the inaccuracy of the robots kick in, the resolution goes a little bit down. So we have around 60 micron resolution when scanning with the robotic system. And here are some examples of scans. So lots of it is carbon fiber, honeycomb structures, propeller. This is the wing from Orly-chan. Foreign objects, some piece of cloth inside, that's also quite, inside the wing, that's quite well visible. And many others. So ceramic heaters, that worked also quite well. Batteries, everything is around batteries. Everybody's scanning batteries, including us. So you can see that here we use 100 kilovolts. Composites were measured with 50 kilovolts, typically the same detector. We don't have to change anything. Welding on aluminum structures, also quite important in many applications. This is a porosity in aluminum, so that's for casting. And high resolution image of a weld. So we newly integrated X-ray tube that has a tiny spot, 5 micron spot, which means we can use magnification and we can magnify the images geometrically, and we can go down to 5 micron resolution in X-ray, 2D X-ray images. It's a bit difficult to do it in CT because the inaccuracy of the robot would spoil it, but in 2D images we can definitely take 5 micron resolution. And this is yet another example. It's a strut of a landing gear of an aircraft. This aircraft is particularly important for me because I sat in it several times. It's from our air club, and guys ask me if I can check if the landing gear is okay. So we took X-ray scan with our system, and for comparison we took also an image on film. So you can see that the difference is clearly visible. So the film, which is very commonly used still for non-destructive testing, including aerospace, has quite some limits compared to our technology. And this is yet another example. So that's a stainless steel part, which is about, let's say, 3 centimeters in diameter. And top image is taken with standard setting of the detector. Bottom image is just increasing energy discrimination threshold. So we can cut a certain part of X-ray wavelengths and use only the higher energies, and that improves the contrast in images, which is again quite important for like computed tomography and many other applications, because you need to have very good input images. That's always important. This is a scan of a painting. I will be talking about it in the afternoon. That's something we measured in Inside Art. The challenge here wasn't so much the physics or the imaging itself. The challenge was that this thing was bloody expensive. It was 400 million estimated price in euros of the painting. So you can imagine that everything had to work 100%, not to touch it, not to scratch it. And you can see that even robots can be made safe enough so that we could dare to scan such a valuable piece. Obviously, we had some extra safety measures like these laser gates, which were connected to the controller of the robot. So, images with focus. So, tomosynthesis explained on this object here. So, if you have a structure like that and you take X-ray image, you get this mess. So all these structures are on top of each other. Moreover, depending how far they are from the X-ray source, they have different magnification. So if you are X-ray imaging something complicated, it might be rather hard to understand what you are looking at, and it might be rather difficult to identify that there are any defects. However, with robots, we can just change the trajectory of the scanning. We already saw it in the previous talk. So we can change the trajectory, how we are moving around the object, and we can, in a way, focus the X-rays to a certain depth. It's not a full computed tomography. It doesn't give you such a good depth resolution as a full computed tomography, but it gives you good enough depth resolution to separate structures from each other. And that turns out to be quite important because A, it's much easier to understand the image, B, the kind of defect detectability goes up because you can separate these structures from each other. And there is another benefit. There was also a question about measuring these dimensions. So in this image, it's rather difficult to measure anything because you don't know the magnification. But after the processing in the computer, we have everything on a scale, so you can do basic metrology here as well. So this method applied on a honeycomb, which is commonly used in aerospace. You have focus on one side, you have focus on the potting around the insert, and you have a focus on the other skin of the structure. Here, another honeycomb just with water in those cells. That's a big problem in aerospace. You have to avoid it because if there is a water in the honeycomb and the aircraft goes up to high altitude, it may freeze and it may cause a damage of the honeycomb. So water detection is quite important. And in this scan, we saw this kind of weird pattern. We didn't know what that is, and we were wondering if we have some problem with the detector, and it turns out to be a description of the sample. So it just can give you an idea how good image the camera can measure. This is yet another example of the tomosynthesis. It's a carbon fiber propeller for eVTOL aircrafts, so for these aerotaxis. And left is 2D image. So the propeller has a like laminated piece of wood inside in the center. Don't ask me why wood, but that's how they do it. And here we can see quite easily these big cracks between these segments, but not really anything else. But in the tomosynthesis, we start to see also these hair cracks around the insert. It's the same scan. This picture is the same scan. Just the gray scale is changed to see the layering of the composite. So here are the layers of the carbon fiber in the same image. Yeah. And back to our aircraft. Here, because we applied the tomosynthesis, we can see how deep the crack is. So not only that there is a crack, but we can also estimate how deep the crack is, and also what is the shape of the crack in the different depth. Now there are some limitations. As I said, you don't have such a good depth resolution as in case of computed tomography, so that can be sometimes handicap. On the other hand, the tomosynthesis is good to measure region of interest of something really large. If you have a link, then this is a very good method to use it. Yet still, if you would try to visualize the data that you have measured in 3D, you get something like this. It's a cube of mass. You cannot really visualize it in 3D. And that's why we combine the tomosynthesis scan with like laser profiling. So we measure the outer shape of the object and we sort of carve out the real structure from the tomosynthesis. And then the result is something which is very much close to computed tomography. Okay? That very much increase again the readability of the structure. And for that purpose, in order to measure the shape, we have integrated this little laser tool here which measures the distances. So the robot first scans the shape and then we use that within the reconstruction. Now, if the structure allows, if we can rotate around, we can go to full 3D. So you can see guys are moving again the system to the aircraft, positioning it freely. This is a big advantage of the collaborative robots. I forgot to say that we are using universal robots, so those are meant to work with people on production lines. When they feel a collision, they stop. For us, it's not really advantage for like preventing collisions with humans because anyone can be around when the X-rays are on anyway. But it is very useful to prevent collisions with the sample. And also, it gives us an option. Can I go back? Yeah. We can also manually position the robots in the location. That's quite a big benefit. Nevertheless, so the system. The source detector rotates around the object and we measure full CT as we saw in the previous talk. And here are the results of such scans, all sorts of things, again honeycomb. In this case we have stainless steel pipe inside the honeycomb, so we were able to suppress all kinds of artifacts that are normally present, automotive parts, even some preclinical research. You know, the application range is very, very wide. Some first results for medical applications, so it's vertebra, it's a 3D printed piece, and we were testing on how far we can go with the resolution. And the automotive bits and pieces, Czech Republic is of course big on automotive, so detecting some porosities in here. This is a nice stuff. The real thing we cannot show, so it's just a surrogate object. Let's say that you have a structure of light materials, and then you have a fastener which is of titanium or steel, basically something heavy, and you have a defect underneath that. So if you take a standard X-ray image, any defect is kind of shadowed by the high attenuating piece of the material which is there. You can see stuff only if it's protruding from beneath the head. But because of the flexibility of robots, we can sort of peek underneath the fastener head, and we can look around the fastener, and we can see any kinds of defects or foreign objects all the way to the screw or the fastener itself. So that's really beauty of robots and flexibility it gives you. This is yet another example of glider wing, and in this case we measured only 105-degree range, so we couldn't measure full computed tomography. Yet still we are able to see all sorts of defects and porosities in the leading edge, even some sort of dent in the layering. And if we do 3D visualization, we see it looks like somebody pressed a finger against the layers when they were putting it into the mold. Now, I mentioned the robot-to-robot calibration. So one way is to connect them mechanically and calibrate the mutual position of robots, but that's not very practical if you have really a large aircraft and you would like to have one robot inside, the other one outside. So for that purpose, we have developed a method to calibrate using X-ray beam. The beauty of that method is that it's independent of the structure. So even if you are shooting through something complex, still we can calibrate the mutual position of robots, and then we can use them for the computed tomography. And then there are lots of other methods like X-ray backscattering. Again, you will hear in other talks about these methods. The point is, for example, in this case, that we can have both X-ray source and detector on the same side of the object, and we can scan from one side with X-rays. That's one benefit. Second benefit is that we can measure, for instance, gaps between large panels, something which otherwise would not be visible in X-ray transmission mode. Ultrasound would tell you that there is a gap, but it wouldn't tell you how large the gap is. But this method can tell you some estimate how large the gap is between these panels. And because we have robots, we can scan and we can do some clever approaches, and we can measure single-sided computed tomography if you want, with the backscattering. Ultrasound, that's another one. Even though we are very X-ray centric, we have to admit that there are situations where the X-rays are not the good answer, even the backscattering, such as here. So if you have impact damage in carbon fiber, then X-rays will not really tell you anything. But ultrasound will tell you that these layers are detached from each other, so there is a delamination. So it really makes sense to combine these methods together, because each is showing you something else. And for that purpose, we have integrated so-called laser-excited acoustics. So that's a method where you have excitation laser which hits the surface, generates a shock wave that propagates through the object, and then we are listening with microphone from the other side. Robots are important in this case because, especially in aerospace, nothing is flat. Very few parts are really flat. So robots are good to navigate along the curved objects. And more modalities. X-ray diffraction. This is something we believe has a massive potential. Again, Jan Jakubek will be talking about it later today. In this case, you can see X-ray diffraction pattern measured in and outside of the heat-affected zone of a valve. You know, that's something which is really has a massive potential for all kinds of applications in production. And then Dr. Kotterli will speak about application in forensic analysis. So for that purpose, we are adding more modalities, such as all kinds of hyperspectral cameras, X-ray diffraction, as I said before, and X-ray fluorescences, and more hopefully will come later on. So again, you will hear about it in other talk. And software. Everything is revolving around software, so I think we did already quite a good job in developing user-friendly software that shields you from the complexity of robots and still gives you a good option to, or good flexibility in measurements and data reconstruction and calibration. All that is quite important. And so to wrap it up, sometimes we are joking that we are building like a Swiss knife for non-destructive evaluation. So you attach to the robotic platform the modules that are suitable for your job, and then you do your measurement and you choose whatever is suitable for your case. So thank you very much.
Thank you very much, Dr. Uher, for your provoking speech, and now it's time for another discussion. Please again wait for the microphone, raise your hands. I see Sasha Schenk asking.
Thanks, Josef. Very nice talk. One question concerning the mobility of your system, and it's also a bit of a question to Gabriel concerning the drones. How mobile is it when you have to attach like a tether or a tethered system, because you have to have a power plug at some point? Probably it's not, maybe it is working with a very mobile battery solution also?
Well,
for some minutes at least?
Well, in principle, yeah, you can power it. The theoretical maximum consumption of the system is about 2 kilowatts, but that's theoretical. You know, in reality, the consumption is much lower. So you can have some sort of batteries or some petrol generator, electricity generator. You know, so I don't think that the power is an issue. Truth is that the system as is now has some limitation in the portability, because the pedestals, for example, that we have under these robots are quite heavy. So we are now working on ways how to make it even more portable, have some sort of tripod like we have here. You know, it has to be more robust, of course, but something that would let us to set up the system within 15-20 minutes, you know, to get it ready for the measurement. You know.
I see many hands. Okay, thank you.
Hi, Josef. Yeah, nice talk. I think it's really interesting how you're able to do the material differentiation. And I was just curious on, how's that performed, and do you have to do any kind of calibration?
Well, There will be more about the material differentiation in the afternoon, because we use that quite a lot for art inspection, because there, pigments are of all kinds of types. And so we are using changes in X-ray spectrum. That's the beauty of these detectors, that we can measure X-ray wavelength or energy, and we can use that to recognize sort of like the trace of the material. Yeah. So that can be used. There are, of course, some limitations. If you are talking about plastics, it's much harder, because it's always carbon, oxygen, hydrogen in different combinations. So that's more difficult to recognize. Once you have some heavier elements, then it's easier. So that's a really broad topic. Again, Jan, I think you will be talking about it. Yeah, he's nodding, so he will speak more about how to use these detectors and what kind of detectors are there. Because different jobs may require different detectors to discriminate materials.
Okay, thank you. And a second question was, so you on your tomosynthesis work, you were basically taking Z depths, and you said the resolution isn't good, but what is that resolution like roughly in terms of Z resolution?
Well, that's a little bit difficult question, because the depth resolution also depends on the size of the feature you are looking at. Yeah, because try to imagine. So you have this object, and you would like to see what's behind it. So, and if you have only limited range of angles, then you don't really, if it's too close, you will not see it. Yeah? You have to increase the angle to start seeing it. If you have it the other way around, then it's much easier. The pen you will see even from small angles, you will get the depth resolution. So that's one of the limitations of the tomosynthesis, that you have that sort of like dependency. Having said that, there are groups. There is actually a group in Texas and University of Arlington, and they seem to have a nice tool how to improve the reconstruction. So that's something we can talk about. And also there are other options for the future as well.
Okay, thank you.
Thank you very much for your questions. First hand was raised over there. You have the speech.
Thanks. Brilliant talk, as always. No, but two questions. First of all, you were talking about laminography, but of course you're not limited to linear laminography with the robots, right? So you basically can do like some sinusoidal additional data acquisition. How much do you estimate the gain by having this additional freedom in laminography to?
Well, first of all, it's a very good question. First of all, one issue I see around the robotic systems is the terminology. Because, with the flexibility of robots, you can combine all sorts of approaches together. You can have 2D imaging combined with just parallel movement of detectors. You can add some angles. You can have a helical scan, cone beam scan. Everything can be on one pile. So first issue is how we speak about it. And that's number one. Number two is, obviously, again, as I was here explaining the tomosynthesis, it's all about like what you are looking for and how many angles, how many points of view you add. In my opinion, the robots or the robotic approach has the benefit to sort of mimic how humans are looking on things. If you have a glass with water and you would like to see bubbles inside, that's an example I always use. We also don't rotate like 300 degrees, 360 degrees and do some CT reconstruction in our mind. We look from several angles and we get the idea what is where. Yeah? And we keep adding the angles until we think we have a good idea about the 3D structure. So with this technology, it's exactly the same.
So it could be real-time adaptive scanning at some point, basically, where you say, okay,
yeah,
I want to look at this feature, I basically
that
refine this trajectory in real time, basically saying, okay, this is, and this would be a very strong interactive system, right? Because
absolutely,
it would be very natural to operate.
Absolutely. Actually, at some point, we had also like an option to control the robots with a 3D joystick. So, and there were many situations where just live image was enough. We had a guy who brought a bike frame, and he knew what he's looking for, And he just took the joystick and he was like looking from different angles, and then at some point he said, yep, okay, that's good enough, I know. Yeah. So I can imagine that a similar approach could be used as well. So you would have the operator who knows what he's looking for, and he will keep adding like projections up to, and somewhere the machine will be reconstructing, you know, and at some point, you know, the conclusion would be, yeah, that's good enough. Or it can be AI controlling it.
Okay, and I don't know, I'm just curious, how do you align the tubes? Do you have like a cross-slit collimator, or do you have some fiducial markers? Or you said you can align?
Yeah, we have a collimator, and then the robots do a dance around the collimated beam to find out the mutual position.
Thank you very much for your question. And I saw originally another two hands. Yeah, right. Dr. Ebert, please.
I have a little bit exotic question. We have tested the first ADVACAM detectors, and we could nicely see traces of muons. And the use for myography was not very good because the detector was too small. Now with your robot, you can scan a large area. Did you ever try to do that something for myography? Because it's upcoming with new detectors.
Not yet. But you are right. It could be possible. It could be possible to do something like this. The question is time. You know, how much time you have for the measurement, because it will take ages.
You need weeks probably. There was a fantastic project for the pyramids. They got some millions of funding, so that's precondition, I guess.
Look, we are open to anything. You know.
Thank you very much.
Regarding the strategic point of view, regarding the size of the sensor, to how quickly you can scan. Is it also, so we also use Medipix 3 in a Fear 1 configuration from ADVACAM. Does it make sense to go to bigger formats? Or is the data or the cost really a killing factor?
Actually, also a very good question. And we get it quite often. Yes and no. If you have a larger detector, and let's say you are measuring the tomosynthesis, so source and detector are moving together, that's the easiest approach to the tomosynthesis. Then having a bigger detector means you have kind of wider range of angles, yeah, from the larger detector. But still the stepping you should keep small, because that gives you kind of the fine step in the angles. Yeah. So bigger detector doesn't really speed up the measurement, but gives you better data in this case. Yeah. And it very much, however, if you have 2D image, of course, then the source is stationary, and then you can measure with larger step of these tiles, so there it speeds up. You know, so it's kind of like yes, no, depending on the situation. And truth is that the speed of the measurement is definitely a topic. That's why guys in Tegendorf are also working on that continuous move and all that. Absolutely, you know, speeding up the measurement is a big topic.
And one last question regarding the scintillator from cadmium telluride. What do you think are the challenges for the high power applications? Or in case we move to higher energies, where do you see the limitation, and where is the sweet spot for resolution to the scintillator?
Well, because it's a direct conversion, so the radiation is changed directly to a charge, which is processed in the pixel, and the charge is attracted by the electric field applied. You know, there are much less pronounced effects like the light. There is no light spread. You know, this charging and so on. So, what that means is the detector can go to much higher energies compared to just charge integrating devices without any trouble. So you can really use the same detector for composites with tube set at 50 kilovolts, 40 kilovolts, but you can take the same detector and use it on accelerator with 3 MeV, no problem. Yeah. So from that perspective, there's not really a limit.
All right, we have maybe time for one last question, if there is any. If not, I would thank you, Dr. Uher, for your speech.